Hi, it's great to be back. Actually, I did my PhD study here from 91 to 95. Uh, my supervisor was Peter Eggleton. Um, Now I'm working in Kunming. Oh, that's not the right version. In my new version, I have my email address. I was thinking, so if anyone had a chance to visit Kunming, just drop me a line. We can have a drink together. Uh, Jane just talked about binary population synthesis. Now I'm mainly talk about the binary evolution and the observation of binaries. We know that 50% of stars are in binaries, or more. To be more extreme, we can say that most of the massive stars are in binaries. Binaries, they have interactions, and that makes the evolution more complicated. Binary evolution produce many exotic objects, such as type A supernovae, double black holes, double neutron stars, millisecond pulsars, actually binaries, and lots and lots. Here, that's the binary evolution tree that we plotted in an article published by Research in Astronomy and Astrophysics. That's a, that's a special issue for the 20th anniversary of RAA. So the binary evolution, there are lots of channels for the evolution. They can produce uh, LIGO Virgo sources that double neutron stars or double white dwarfs, type A supernovae, and lots of things. So binary evolution are very complicated. However, there are two major problems for binary evolution. The first one is, so when for a binary system, when the binary evolve in the primary field is Rauschenloop, so we have mass transfer. The mass transfer can be stable or not. If the mass transfer rate is not that high, we say that's stable. If it's too high, then that's not stable. If the mass transfer if it's stable, then we can get a wide binary. If it's not stable, the binary system can suffer, can form a common envelope. The common envelope is something like this. The the envelope engulfs the core of the primary and the secondary. So um, actually, common envelope is, I think, that the least understood binary process. So actually, it was proposed by Pashinsky in 1976, and all kinds of most of the interesting objects, say double white dwarf, double neutron stars, double black holes, are from common envelope evolution. So those two problems are not well understood. Um, for the first problem, the mass transfer instability, because in the past, for most of our studies, we use polytropic model. But we see later that the polytropic model, the results from polytropic model are not consistent with observations. Then later, Hongwei Ge in the audience, when he was my student from 2005, he worked with Ron Webbing. Ron Webbing was also a PhD student here from the 1970 to 1975 or something. And we together, we uh, uh, developed models for adiabatic metal loss and the thermal equilibrium mass loss. By adiabatic, we mean the mass loss process is adiabatic. By thermal equilibrium mass loss, we mean during the mass loss process is in a thermal equilibrium. We just rewrite the basic equation of stellar structure, and it took us for the last 2 decades. Now it's more or less established. So if we compare the new criterion, there are very big difference. For a polytropic model, if for a binary system, if the primary is a red giant, the mass transfer is always unstable, dynamically unstable. But in our new model, that's not the case. So I can show you, we made a comparison with double white dwarfs. So we can see that for the old criterion, so we can get a binary with a very tight orbit, or we get a merger. But in our new criterion, that's different. So we can see here that's a model. That's our prediction for the merger rate of double white dwarfs. So we can see the solid line here. That's from our new model. The dashed line that's from the polytropic model. So we can see that our model is much better. We also do something about the observation of binaries. We know Parshiniki proposed the common envelope evolution, but then the common envelope is very short-lived, just thousands of years, and the process is dynamic, so it's very difficult to see it. So we use the sky mapper. We have a project that's J1920-2001. We found a hot sub-binary. Because hot sub-binary, that's from common envelope evolution. For this, for such a system, if there is a common envelope ejected, the velocity, the envelope velocity is something about 200 kilometers per second. So from the spectrum, we found a p signal profile. From the profile, we did see calcium K length, because that calcium K length, okay, that's we see that this envelope. So we see the direct evidence for this. So and then later we search for LAMOST spectra, because for common envelope evolution, not all the materials can be ejected. So there should be some circumbinary material. I think we believe we found them. And also, Jay just taught in her B path. For the B path, there is something input that the properties of binary population. So about the binary fraction, mass ratio distribution, and the orbital period distribution. And we use the LAMOST data. We see the binary we have a higher binary fraction for early type stars, and for more metal-rich population, the binary fraction is higher. And also, we developed an approach we call the PAR approach, because in the past, when we want to derive the mass ratio distribution, we need to use Kepler law. We need to use to measure the multiple epoch observation. But for our power approach, we just need one spectrum. So we did a cross correlation. That's the spectra with a solar spectrum. So we have two components. Each component corresponds to one for the primary, one for the secondary. So the peak amplitude that's correspond to the luminosity. Luminosity connected to mass. So we got a relation of the peak peak amplitude ratio with the mass ratio. So we got the mass ratio distribution. We noted there is a twin phenomena for G-type stars. And also we applied our method to triples. So we also got something like this. So at last, that's advertisement for research in astronomy and astrophysics. So currently, the impactor is 1.8, but we published a paper last year, the nanohertz gravitatory waves. So this paper got lots of citations, it's more than 500 already. So we will see next year the impactor will be something like 3 or 4. Thank you very much. Yeah.